Hello and welcome students. Good evening, good morning, whenever you're watching this video. This video is going to be on electrochemistry. I do apologize this video late to you. As you know, I've been helping you guys study for finals and such. Quick thing, little housekeeping thing. Remember that this lab is due the 25th of April, so you might have about 2 weeks to do it. The lab is very, very simple. I'm going to show you the lab right now. So I am wait a second. There we go. So technically, I am using other students' from another class's data, so you can't copy me word for word. If you need to use data, let me know. I can give you the person's data. But, okay. Sorry, if you hear barking, it's my dogs fighting over food. Okay. As normal, fill this out the best you can. I'm not going to really even grade this. This is not really that important to me. Okay. Here is something you guys should have written down. That's good. Know, though, please, that one of the solutions is going to be zinc. One of the solutions will be copper. Again, I am writing by mouse, so I do apologize for bad handwriting. Hopefully, after the semester is over with, I get my computer fixed and videos will be better from now on. This is a concentration of 0.5. This has an unknown solution with X or Na. Again, bottle information I don't care about. Okay, moving on. This is the stuff you guys should have done. Oops, sorry about that. This is the stuff you guys should have done. It's this stuff right here. This is the concentration after diluting the copper solution. Here is the voltage you got. Fill that in. All of the female students I have is in millivolts because they're 2 to filter 2. I don't care if it's millivolts or volts as long as you keep consistent. It doesn't matter to me too much. Okay. This one right here, you're going to have to solve for mathematically, and it's very simple. You're just going to take the natural log of 0.5. Oops, again, that should be 0.5 concentration, 0.05. Over the concentration of copper. So that concentration of copper comes from this right here. You plug that in, you're gonna get that. Once you guys got that, either you go to Logger Pro or you go to Excel and you're gonna plug the data in, take the data, insert graph, add chart elements, we're gonna add a trend line, add a linear trend line. We're also more importantly going to want to display equation and display R value. Okay. Now I told you guys in class, but it's been a while, so you may have forgotten. I'm going to make my pen smaller so I can write more neatly. Remember that the Nernst equation is E is equal to the E of the cell minus RT and F. And then you have the ln of K or Q. Please note that the negative RTNF is going to be our our slope. Our slope is negative because our RTN is negative, so it should be going down. And our Y value is going to be this E naught right here. There we go. So knowing this information, we can take this and we can enter the data down here. Boom. Y value, X value. That is going to be your experimental. That is what you found. Now, in the reading you should have done for this lab, as you're supposed to, but I'm going to do the reading for you because the reading sucks, is you have E naught. It doesn't suck, it's just very boring, very dry. So you always should read your post lab and pre lab. So E naught, remember, is the energy of reduction minus the energy of oxidation. We did the lab, and we went from zinc to copper. So copper is being reduced, zinc is being oxidized. If you go look at the notebook or go look at the charts, you can find the energy of reduction for both copper and zinc. Copper has energy reduction, or if you want to write it this way, as you guys have seen it in class, is +2 plus 2 electrons gives you copper. Zinc plus 2 electrons gives you zinc. The energy for this guy right here, the energy for this guy is corresponding to this. 0.34 and minus 0.76. So if I change my color to red, energy reduction, or 0.34 minus 0.76. Can you subtract by negative, change the sign, boom, boom. I was like, look at 0.1. That's how you do that. Now, RT and F is you just plug it in. R, T, and F. R and F were constants. We're going to use those right now. That translates into 8.314 times the temperature, which is 25 degrees Celsius. Sorry about that. Which is 298. Sorry about that. 298. So the electrons exchange. As you saw, 2 electrons were exchanged in this previous thing. So 2 times 96,500. Figure that out. Bada bing, bada boom. Goes in there. Okay. Next is the unknown. The unknown is going to be a calculation based off the charge. Whatever one is closest to, the student said it was close around here, so we assume with that one. Boom, plug that in there. Simple as that. Or if you wanted to, you can assume, save yourself a lot of work, but if you want to be very accurate, you can solve it using the Nernst equation. You're just solving for this x variable, given your E naught and your RT, plug that in, you can solve the concentration. Do that, or you can kind of guesstimate whatever one's close. If you don't have a voltage close to any of the ones up here, you're going to have to use a Nernst equation. I do apologize, but it's always best to do that. Oops, I do apologize. I forgot to show you. You're going to take the graph. Make sure the graph has everything labeled into it. You guys have been doing good so far. Just make sure you guys know that. The graph's going to go here, just so you guys the graph's going to go. Now it's time for some post-lab questions. So what is the significance of the salt bridge? Well, I told you guys in class, the salt bridge is going to allow for the electron to transfer. Now, normally, it goes from anode to cathode, right? It's going to go from the zinc, which was the oxidation or anode, and the electrons are going to follow, I'll use red, to the cathode, which is copper. But the problem is, this is an incomplete circuit because electrons are only going one way. If we add a salt bridge, which allows some of the excess electrons to flow back into the anode, I now have a complete circuit, thus I can get a very high voltage. That's how batteries work. You complete the circuit. And that's what you're going to say. You're going to say the salt bridge completes a circuit which allows the anode and cathode to communicate both directions. Okay. Here, you should tell me if it's oxidation reduction. So remember, if oxidation is loss of electrons or oil rig, reduction is gaining electrons. It's the rig, or if line goes GR, either one. You need help, oil rig, or you have Leo goes GR. Oxidation is losing, reduction is gaining. Loss of electrons is oxidation, gaining electrons is reduction. So this one right here, I'm losing electrons, oxidation. Where does it take place? The anode, always, always, always. Hey, what's this one? This is reduction. Where does that take place? The cathode. Always, always, always. The rest you can do, you do the last two on yourself. Just want to show you what's going on. Okay, up next we have this. Question 3, if the concentration of the thing was changed from 0.5 to 0.25, what would happen? Well, that's actually pretty easy to see. And what would happen is nothing. This is my slope. Where is concentration in here? Concentration is not there. Thus, I could change the concentration. I can dilute to a degree. I could make it super concentrated, where it's basically just super copper. Wouldn't affect anything really. Remember, E naught is just the energy potential. That's set for copper and zinc at 25 degrees Celsius. The only way I can change it is tweaking the temperature a little bit. So that also has no bearing. The change in concentration does not have bearing on the slope at all. We did it just to see what happens, but nothing happens. Okay, you're gonna use the Nernst equation. So that's gonna be E naught is equal to minus RT and F ln of X, or sorry, not ln of X, my bad. Ln of K or Q, whatever you want, but K. Remember that K is the concentration of all your products or the concentration of all your reactants. Bada bing, bada boom, bada bing. You notice that copper solid, does it have anything? Because it doesn't do anything. Boring. Okay, next is E naught. You figure out which being oxidized, which being being reduced. You can kind of tell based off that. Iron went from 1 to, sorry, from 3 to 2. So it gained an electron. So it went from nothing to nothing. Interesting. You can figure it out, the rest. If you're solving for E, let me know. You might have to balance the equation, hint, hint, wink, wink, because you notice that this one is doing 2 electrons, this one's doing 1 electron. They're not equal. You do have to balance it. So wonder how you would do that. Wink, wink, hint, hint. Yeah, number 5 is use the information for question 4. Okay, so we basically just use this equation right here. Yeah, to calculate Gibbs free energy and change enthalpy. Well, change in enthalpy is a change in system or status or formation or something. It's just changing chaos. I have an aqueous, a solid. Remember, solids have the lowest, aqueous have the second lowest. It becomes an aqueous and aqueous. Oh, well, I become more random because I got rid of that solid, which means it's going to be positive for delta S. Well, there's going to be math in there, it's not really given anything. You just tell delta S is positive. If delta S is positive, right? Delta S is positive. It eats it. It's bigger because we get more randomness. We make 2 aqueous solutions. Okay. Delta G is, if you can tell, you get your value. Your E value should be positive. If E value is positive, delta G has to be spontaneous or negative. It's a correlation thing. Or you could just have to solve it, which you have to use this equation. You'll get a negative number because all of the other numbers should be positive. Thus, positive times positive times positive times negative is all negative. But that's what you have to do for this lab. It's very, very simple. I think these last 2 problems are going to be the longest. Please make sure you get to me by the 25th. I am going to go start making your kinetics one right now. If you have questions, please let me know. Reach out to me by email. Thank you. Have a good day. Pretty much answer that question too.